Hello everyone and welcome to Texas Tech University's Project Lab 1 tutorial videos. I am one of the tutors for this course. My name is Daniel, and in this video I'm going to be showing you how to program the 7-segment display on your BASYS3 board using multiplexing method. And first, let's look at our BASYS board. So on our BASYS board we see that we have 4 7-segment digits on our board. So if we go to our data sheet, so I just googled BASYS3 board, click on this digital link and open up the data sheet. Here in the data sheet we scroll down to the bottom and here is the 7-segment. Alright, so as you see we have 4 digits on the BASYS board. Each digit here is represented by anode, so this digit would be digit 0 or anode 0. This digit would be anode 1 or digit 1, and anode 2 and anode 3. So what we see is that the anodes represent each digit, so again digit 0, digit 1, digit 2, and digit 3. And then the cathodes are the segments, represent the segments. So as you see, there's cathode A through cathode G through decimal point. So those represent the segments A, B, C, D, E, F, and G, and decimal points. This is the standard configuration of the 7-segment display. You always have the segments going in A, B, C, D, E, F, G, and decimal point in that configuration. Okay, so the next thing we want to do is go back to a new Google page and search BASYS3 7-segment multiplexing. This will bring you to a few different links. They all have example on 7-segment multiplexing. They're all great resources. I've used Stack Overflow for various different Verilog modules but the one we're going to be looking at is the simple fpga.blogspot.com learn Verilog by example. So open this link and we come to this page. So we're going to have to give credit to simple fpga.blogspot.com. They do a great job explaining how the multiplexing works on the BASYS2 board. They go into depth on counters and the clock that runs the BASYS2 board, and then they give us great example code that we can copy, paste, and adapt to make it fit to our BASYS3 board. Alright, so just if you want to get familiar, you can read through this page. I'm going to go ahead and summarize it for you. So pretty much what multiplexing is instead of having 8 connections to each one of these digits and having them all on at the same time, well, the technique multiplexing allows you to turn on 1 digit at a time, and you just do it in a fast sequential order to make your eyes think that all 4 digits are turned on at the same time. So multiplexing is a pretty unique technique that reduces the number of input-output pins and allows you to still do the same thing we want to do. So as you see, if we had 8 connections for each, we would have 32 connections. So multiplexing allows us to only use 12 connections. And then the next thing we see here is that the 7-segment display on the BASYS2 and BASYS3 boards are active low systems in which the 0 is required to turn that segment on. So as an example, they have this great figure here. You see that they are producing this 3 on the digit 0. So to turn on digit 0, you see that there's 0 on position anode 0, and then all the rest of them are 1, so therefore they are off. And then you see the segment pattern here. So to create the digit 3, the only segments that would have to be off would be E and F here. So again, A, B, C, D, E, and F, and G. So E and F would be off, and the rest of them would be on. So again, zeros are on, ones are off, and the decimal point is also off. So that explains that 1 at the decimal point. Alright, so that explains the cathodes and anode inputs of the segment display. And multiplexing, again, we're just gonna light one digit at a time, and we're gonna scroll through fast enough to trick your eyes into thinking that all 4 are lit up simultaneously. So it says here that in order for that desired effect, we need a refresh rate of at least around 1,000 hertz. I made sure to say around because it doesn't have to be exact. Here what they do is a 50 megahertz clock that's on a BASYS3 board, and they use a 16-bit counter, so 2 to the 16th will account for the 16-bit in binary. And if you do that calculation, it comes out to about 800 hertz. So if we do that calculation with, let's pull up my calculator. And if we do that calculation with 100 megahertz, 2, 3 divided by 2 to the 16th, what do we get? 1,525. So that's still pretty close to 1,000. It's a little bit over, so it's a little bit faster. We could adjust it to do 17 bits, and I'm sure 17 will give us around that 800 hertz. Or I've tried it with 16 bits and it works fine on the BASYS3, so we're going to move on with 16 bits. But what you see here is that they are saying that they're using 16 bits to create the 800 hertz counter, but then they're adding two bits so that they can use those 2 bits to toggle through the 4 different positions. Alright, so to demonstrate that, again, I'm going to pull up my calculator, and I'm going to set it to programmer and binary. So now let me demonstrate a 16-bit counter. So as I fill this counter up, you can just think about just time incrementing this counter, and the counter fills up. So now it's full. So if we add 2 additional bits, so let's look at these 2 additional bits after our 16 bits. So this is 17th and 18-bit. So let's see what happens if we add another 16 bits. So another counter gets full, and we add it to it. So as you see, the 2 bits at the very front went from 0, 0 to now 0, 1. So that's what they're talking about, the 2 most significant bits, and they're going to use it to toggle through the 4 different digits. So we're going to start at digit 0, then move to digit 1, then to move to digit 2, and move to digit 3. But since we have a counter that's filling up, so let's add another counter. So plus another counter is filling up. So while this counter fills up, that light is actually lit up on that digit. So right now we're at digit 1. So digit 1 would be lit up its appropriate pattern until this counter fills up, which would change those 2 bits to now position 2. So now it would be in digit 2, and the counter would continue counting. So counting, fills up, and moves the second digit to position 3. So now we're back at, or now we are at position 3, digit 3. And if you continue this however many times you want, so let's add another counter, fills up, 16 bits, boom, fill, you add it, and now you see that these reset back to position 0, which go back to this digit 0, and adding it as many times as you want, you'll see that these two bits, the 16th, so 17th and 18th bits, just toggle through the 4 desired digits. Alright, so that is what they're doing here. So that's why they have an 18-bit counter, and they're using the 16 bits to count, and the top 2 just to toggle through the 4 desired digits. Alright, so now we can look at the code. So we can go ahead and open up our Vivado software. So we can double click on it, so yes. Alright, so it's open. Now we can create a new project. We're gonna hit next. We'll give it a name. I'm going to call it 7 seg tutorial. Hit next. We want it as an RTL project. We do not specify sources at this time. And then we have to select the FPGA that we're working with. So family, we're going to go to Arctic 7, package CPG 236, speed grade -1, and then from the remaining 3 you're going to pick this XC7A35TCPG 236-1. Hit next, finish, and this will create an empty project that we can start adding sources and creating modules and doing everything we need. Alright, so let me just squish this down a little. Work over here. So this is a blank project. First thing we want to do is go here to sources and click on add sources. We want to make sure we select add create design source. Hit next. And then here we want to create a file. Type is Verilog. File name, we'll call it 7 seg tutorial. Alright, so highlight it and hit finish. And here it wants you to label your inputs and outputs. For now we're going to hit OK. Yes. Alright, so that should have created a module. Put it into your sources, and you can double click it to open it up. So here you can maximize your module or your code here, and you'll see that it's just an empty module, just the standard header with the standard time scale and the module name, and that's it. So what we want to do is go back to the simple FPGA Blogspot link here, and we want to copy everything from line 2 down to line 80. 2 to 80, Control C. It is important that you copy from line 2 because you don't want to copy the name here, since we already have our own name. So we're going to highlight everything below the title and replace it with what we just copied. Then verify that it's been copied correctly. Here at the bottom you should see 1 in module, and it should be purple like that. Then you want to scroll up to the top and check the name here. Make sure that there's only 1 open parentheses that goes with your 1 close parentheses followed by a semicolon. And make sure that you only have 1 name. And once you've done that, then we can start moving into reviewing the the Verilog module here. So finding example code online is a great way to learn how to code and learn how to make modules. However, the biggest warning I'll tell you is that you have to make sure you understand how everything works, or else if you don't understand how everything works, you're not really learning and you're just copying stuff. So to show you how everything works in this module, we're going to start by line 1 here and looking at the inputs. So here we have two inputs, one's called clock, one's called reset, and since there is no specified size here, then they are both default 1 bit. So we have 1 bit clock and a 1 bit reset. 1 bit clock, we will attach it, we will connect it to the oscillator that runs the 100 meg clock on the BASYS3 board, and this 1 bit reset we will connect it to a button on the BASYS3 board. Alright, so now moving on to these inputs, we have N0, N1, N2, and N3. It says here in the comment that these are the inputs for each display. Alright, so that's a little bit vague, so let's continue looking through the code to see exactly what IN1, IN2, IN3, and IN0 are. So if we scroll down, we see here that IN0 is used to go into SSEG, IN1 goes into SSGG, and it looks like they all go to SSEG. Okay, well, let's see what SSEG does. Scrolling down, we see this lookup table, or this case statement, however you want to call it. But we see that the argument is SSEG. So our ins, IN0 through IN3, go to SSEG, which set the bit pattern to display here. So SSEG can be any digit from 0 down to 9. So that means we have to make sure SSEG is big enough to hold a value from 0 to 9. So that's 10 different values. So we got to make sure SSEG and IN1 through IN3 are big enough to hold 10 digits. Alright, so that is all of the code there. We don't see SSEG being used anywhere else. So now thinking back to digital systems, 1 bit can only go from 0 to 1, 2 bits can go from 0 to 4, or 0 to 3, and in order to have a register big enough to hold a number from 0 to 10, we're going to need 4 bits. So to make these 4 bits, you open brackets, put the most significant bit first, and then the least significant bit. Close brackets. So this little statement just says that each of the following is now going to have 4 bits. And the bits will start from the left will be the 3rd bit, from the second left will be the 2nd bit, 1st bit, and 0 bit. So each one of these is a 4-bit array, and it has position 0 all the way to position 3. Alright, so now we know what those inputs are, and we've made sure that they are the right size that they need to be. So now we can move on to these outputs. Here, these are kind of trivial. You can see they say A, B, C, D, E, F, and G, and decimal point. So, and the comment tells you that they are the 7 segments of each individual digit. And this one right here, this output, is also pretty trivial, as you can see that the AN stands for the anodes, and they correspond to the 4 digits that are on the BASYS3 board. So those ANs, you can kind of think of them as being these ANs. So when AN0 is on, digit 0 is on, AN1 is on, digit 1 is on, and so forth, so on. but again, we only turn one on at a time. Alright, so that explains that output. Again, it's a vector, 4 positions, and it represents those anodes that I just showed you. This line 30, what this creates is a local parameter, kind of like a variable. It's called variable n. It's called parameter n, and the value of it is 18. For local parameters, you don't have to specify size, so that is the right way to assign the value 18 to the parameter n. And then here we create a counter that is n minus 1s for, so 17 to 0, so 18 bits, because you got to count that 0 position also. So it's an 18-bit counter that allows us to multiplex the 1000 hertz. Again, this is the 18-bit counter that we talked about while we were looking at the binary counter. So it's 16 bits that go up, and then those two most significant bits that change, they move us from position 0 to position 3, back to position 0, and then so forth, so on. Okay, so moving on down, we see this always at block. Always at says that anytime this argument happens, so anytime, whenever, whatever's inside this argument happens, it's going to do whatever's inside this begin and end statement here. So here it says always at the positive edge of clock or the positive edge reset. So that is like the rising edge of a pulse. Positive edge, rising edge, same thing. So what this little block is actually doing, if you look at this begin else or if and else statement, it is actually using the clock to count. So it's counting up based on the 100 megahertz clock on the BASYS board. But if reset is pressed, it will reset the counter down to 0. So then this always at block, all it is counting up based on the clock from the BASYS3 board. Alright, so that, why we need to count, that fills up the counter for the multiplexing to happen. Alright, so moving on down, we have 2 registers. Here they create 2 temporary registers that they're actually manipulating. So in the following always at block here, they are manipulating SSEG and AN temp to be whatever we need them to be. So AN temp, if you actually scroll down, you see that AN temp is just a placeholder to store the information that we want to go to our output AN. Verilog doesn't let you manipulate an output directly, so if we were to replace every one of these AN temps with an AN, Verilog would give you all sorts of error because it does not allow you to assign or manipulate an output as we're manipulating these registers here. So to get around that, we manipulate a register and then we assign it to the output that it corresponds to. So that is a common practice among Verilog code writers. You'll see that in plenty of example codes, and most of them do label them whatever they correspond to _temp. So this AN temp corresponds to the output AN. Again, this SSEG temp corresponds to the output SSEG, or the actual each individual segments down here. Alright, so back to this always at star. So just like the always at block above it, this is just argument. Star means that anytime anything changes, so always at, when anytime anything changes, we would do everything inside this begin and end statement. It scrolls down to here. And looking at this case statement, we see that we are evaluating the two most significant bits of the counter. So n-1 and n-2, we started at position 17 and goes down to 0, so it's position 17 and position 16, which are the two most significant bits. If they are at position 0, we turn on position 0 of our AN output. So AN is, again, this AN temp is a temporary register that is associated with AN, and if you see down here, you assign the register AN temp to the output AN, which is the anodes. So if those two most significant bits, we are in digit 0 of the anodes. If those two most significant bits is 0, 1, we are in position 1 of the anode. And again, 2, position 2, 3, position 3. So this goes back to the thing I showed you with the binary calculator, where it just uses the two most significant bits to toggle us from digit 0 to digit 1 to digit 2 to digit 3. And again, we are taking those inputs and plugging them into the 7 segment appropriate to that digit. So input 0 goes only to digit 0, input 1 goes only to digit 1, input 2 to digit 2, and 3 to 3. Alright, so that explains everything down to this assign statement. And then the next thing you want to see is that they create this register. Again, another temporary register, SSEG temp. So it is used in this case statement to assign a bit pattern that we want to a temporary register, and then assign this temporary register to its appropriate segments that are the outputs. Okay, so as you see, if SSEG is any value from 0 to 9, it'll display the corresponding bit pattern for that digit. So these are the bit patterns that are actually going to the 7 segments. And again, 0s are turning on and 1s are turning off. Last thing, you see that again this temporary register gets assigned to the appropriate segments, and we do a constant assign to decimal point to turn it off. 1 is off. If you want to turn it on, you could put it to 0. If you wanted to get fancy, you could add it here and then add DP over here. But that pretty much explains everything from this module. So now we can go ahead and add some constraints and simulate it, and then program it onto our BASYS3 board. So what I want to do next is go ahead and save it. It'll check for syntax. Once that is done, you want to synthesize it, run synthesis to make sure that there's no synthesis error. And again, you'll see this little status bar at the top right. We can move back to the standard view. And then after this completes the synthesizing stuff, the next thing we want to do is, alright, so it's done, we'll close this. Next thing we want to do is create a test bench so that we can simulate this. So to create a test bench, we're going to going to click into the sources, hit add sources, go to add create simulation source. Next, create a file. We call it 7seg test bench. Again, it's a Verilog type. Okay, highlight it and finish. You can hit OK. Yes. So then you should be able to see the test bench. You want to highlight it here in the source, so make it blue, and then scroll down to the source file properties here. So here in the source file property, it tells you where it all is used in. Since it's a test bench, we only want it to be used in simulation. So we're going to unclick synthesis, we're going to unclick implementation, and make sure that only simulation is clicked. So once that is done, then you can double click on that test bench